Yeah, so I guess before I begin, I can introduce myself a little bit. I'm Chris. I'm a data scientist in Amsterdam, in the Amsterdam office of Booking.com. I work on machine learning. I work on a lot of different things, but I guess my two main focuses so far has been fraud detection and online advertising. So specifically paid search results. I'm not going to talk a lot about the specific applications of online learning, but I'm going to, I guess, sort of take you along my own path towards understanding online learning and really, so also try to motivate why we want to use these kinds of techniques and when they're most appropriate. So I do have to apologize, I guess just like Michal before, is that I really do like equations as well. And I didn't really shy away from putting some in my slides. In fact, it's quite dense. But I promise you that they're not going to be scary, and I'm not going to be too fast. So really just, if you don't understand anything, speak up right away. It's better, I think, to just ask questions immediately rather than just at the end and everything, so you lose track. The goal is really for everyone to kind of to be able to chime in, or at least to be able to understand what the main picture that I'm trying to paint here. So the main question that I wanted to address here is we've all, well, I don't know, actually, can you show us some hands? So, who has been in this situation when you want to do machine learning but your data set just doesn't fit in memory? Okay, that's perfect, okay. So, I want to address this problem, and especially from the point of view where you're not a big international conglomerate, and you don't have access to a very big data cluster, so what do? Right, like how do you attack this problem? Preferably, you want some sort of solution that actually works on your own laptop, right? You don't want to be reliant on some big Hadoop cluster. You want to just be able to run it on your own computer. So this is really the main thing that I want to address here. So let's set the stage a little bit in terms of how do we even begin approaching this problem. So we approach this problem, to make machine learning scalable, by taking our data set and splitting it into little chunks, smaller chunks. And you can do that in several ways, but the goal really is that you learn on smaller chunks of your data, and then afterwards you either kind of walk through your data like in online learning, or you kind of split up your data set and learn multiple models at the same time. Now, so this notion of out-of-core learning is really sort of walking through, so taking one single machine, say, and you just feed it one chunk of your data at a time, and then you go to the next one. Now, this notion of this parallel notion of making things scalable seems to be much more promising, right? Like this should be more appealing to you if I show it to you in this way. Namely, why you only, so if time runs like this, you only have to train. Well, it seems to be a lot quicker. And one of the things that we've actually seen in practice is that this is not really true. This sometimes takes a lot longer than this. And you know why? It's because of latency, and that's not really in this picture. Right, so it actually costs some money, actually it also costs money, but time as well to actually put these things in parallel and to compute this and then to later combine these things. It also takes time. So really what I'm going to try to explain is why this is a very nice route to walk. So like I said, the parallel approach actually does appear superior, at least in the way that I just presented it, right? In this little, it's not, okay, in the picture. And then so, this has actually received a lot of attention in the past, say, 5 or so years. specifically Spark and H2O and XGBoost. There's a couple of things that really allow you to do machine learning so in parallel, right? Now the downside, the obvious downside, is that you actually do need a cluster of a lot of machines, a lot of computers to actually do this, right? Not only that, but you have to have the infrastructure to do it. You have to actually have your data on that cluster, because if you don't, that's another time that you're going to it's going to be lost. Now, of course, it's completely feasible for large companies. In fact, at Booking.com, we have two very large clusters, biggest in Europe, I think. And so we can actually do this. But as it turns out, even though we can, we often don't, because we don't need to. What do we do instead? So we have this out-of-core approach, right? So now, from the way I pictured it, again, it doesn't look superior, but I also feel like it hasn't really received the amount of attention that I sometimes feel like it should. Now, the coolest thing about this thing is this kind of approach actually runs on a single computer, so you don't need to have access to a very big data cluster. Why this is nice, I can imagine that even if you're not a hobbyist, but you actually do want to do this, you're actually trying to make money, but you only have a small startup right now, or you're working at a small startup, and you just don't have the budget to have this very big data cluster. So then this approach will work for you. Okay, so it's not going to be a surprise that this is what I'm going to talk about in this next few minutes. So what are the questions that I want to address here? So this is really kind of the string of questions that led me to sort of unpack all of this online learning, and really this is also the thing that I want to sort of explain it to you in the same way. This is sort of where my interest was really sparked. Let's start from the beginning. So we're actually going to explain quickly what is out-of-core learning, how does online learning tie into this, so what is online learning? Now we know already a little bit about it from the previous talk, of course. Now, how do we apply online learning to batch optimization? So if the setup of online learning is just not necessarily the most natural thing to look at, why does it still work sometimes, right? And the main thing that for me was just baffling is I didn't understand why this worked. Why do people do this? Why do they have such successes with these things? Why are the predictive models that you train with online learning, why do they work so well? And actually, can we do better? So the final thing that I'm going to, the answer that I'm going to address is really give me some examples of how you actually used it in the wild, right? How did we use it at Booking.com, and I'll explain that to you. So the program, here's a little windmill, because of course it's Booking.com, headquarters is in Amsterdam. This is an actual beer brewery where you can go get a beer in the sun. So I'm going to explain out-of-core learning, online learning, talk quickly about online to batch conversion. Then I'll go have a slight sort of theoretical digression to really explain the answer answer the question that I really want to have answered, and then have another look at this online to batch conversion, and then I'll show some business cases. Right, so let's get started. Out-of-core learning. Okay, so like we just said, we have a data set that's way too big, right? It just doesn't fit in memory. It doesn't fit on one memory machine. So what you do is you split it up into smaller chunks, and you sort of feed each chunk one by one. And you have so this is a little pseudocode, which is, there's not much to it, right? So this is the idea. You have some model, and you just update the state of that model. So now, what is the setup of this thing? So let the curly D is really the fixed data set, the fixed distribution, I should say, of the observations that I'm interested in. And so each data point, so each input together with an output, so really, I mean, the goal is to predict what the output is given this input, right? This is sampled IID from some fixed distribution curly D. So a training data set is just some sequence of observations like this. Nothing special about this. It's not unordered as well, so we could just shuffle it up and it doesn't really matter. Now what is the objective? The objective is to minimize the loss, the total loss, where I just phrase it in this way. So the expected loss is the expectation value over this curly D of each single data point loss. So this is a single data point loss. So for instance, if you want to do linear regression, your single data point loss is exactly that thing that's right there, just least squares. Right? I'm expecting this to be known to everybody, so this is not supposed to be scary yet. So now how do we solve this problem? We minimize this by actually doing gradient descent. What is gradient descent? Well, we just say we have our new weights, which are the old weights, updated slightly in the direction of this gradient. And what is the gradient? The gradient is the expectation value over that same curly D of the actual gradients of that single data point loss. Again, nothing really scary, right? Now, ordinary batch gradient descent, what you typically do is you just approximate this gradient by just taking the sample mean of the gradients, right? Now, what is stochastic gradient descent? It's exactly the same thing, except that you take a smaller subset of your data. So you just have a different approximation of these gradients, which might mean that even though you may actually get different, more high variance estimates of this gradient, which often can be a good thing. Anyway, so that's stochastic gradient descent. Is there anyone who's unclear about the details here? Because I think we should be on board. Okay, good. So now, that was out of core learning. So out of core just means don't look at all of your data all at once. What is online learning? Online learning is really something different. So in terms of the previous talk, really, it's this notion where you have, bounded memory, right? So you have some hypothesis that changes over time, where, or at least that's the setup that I'm talking about here, where you really keep updating your hypothesis the more you see. So what do you have here? So let O of t be all of the observations that you've seen up to t, up to round t, right? And then the objective really is to predict the next y given the next x. That's the objective. Now, how do we make that more precise? What are we really trying to do? So, just a quick reminder, the loss that we defined before was this thing, right? This is the sample mean. And now we're going to define something different, slightly different. Instead of looking at the loss, we're going to look at something that is called regret. And why are we looking at regret? First of all, what is regret? So, first, it looks very similar to this guy, right? There's no normalization term in front, but the first term looks very similar to that one. The key difference here is that these samples, these t's, it's actually an ordered sequence of observations. And what do we have here? We have this extra term here, which is just to kind of make the game that we're trying to play a little bit more fair. So that means that, I guess the assumption when you look at regret, the assumption is that there is some special magical theta for which for which if you manage to find where this theta is in your parameter space, you can be what's called competitive. So you can get this guy to be close to 0. In fact, it's not even about it. If you can do better than that too, you can get closer. Okay, so what is this curly theta? This curly theta is just all of the thetas that you've seen so far. That doesn't mean that you really have to remember all of this, but this is sort of the general setup. And this magical theta star is just some reference point, and a very natural reference point is sort of this post hoc optimum. So after you've seen all of your data, after you've seen all of the rounds, you find this optimum here, right? So it's really cool. So this is something. This is sort of an idealized thing that you're comparing it with. You don't really know this while you're trying to train this thing, but it's a good way of phrasing the problem. So now, what is the simplest approach? The simplest approach is exactly what we did before. We just update our weights. So our new weights are the old weights, updated slightly in the direction of this new gradient. Oh, sorry, I think the gradient evaluated at this point. But the gradient is not only evaluated at this point, but also for only one data point. So this is very different, right? This is very different from batch gradient descent. You're calculating the gradient on one single data point. Just one. How high variance is that? That's really shit, right? And it actually works. It actually works. So this is the most magical thing to me. Like, well, how can you expect this to work? So first of all, what really does help is if you want to minimize regret, you can tune these learning rates in a specific way that you actually learn a bit better. But I don't really want to talk about this much. I just want to really emphasize the fact that you calculate these gradients on one single data point. Now, I don't know if you're already puzzled, but let's continue. So when do you use online learning? So typically you use online learning when the consecutive observations that you receive are not IID. And also when you do care about errors that you make early on in the learning process. So the thing that you're not interested in is how well does my eventual model do, but I really want to learn as quickly as possible. I want, the errors that I make early on, I want to really reduce those too. And so that's really in this notion of regret. And so this I'm always a little bit not so sure about. But typically you want to say, okay, I want the state of the environment to be able to change underneath me. As I'm learning, the state of the environment may change. Now that really changes things a lot, right? So we can put some very specific sort of mathematical notions on it, but I think what's easier to an easier example to understand is spam detection. So the underlying state of the environment changes because you learn the rules to block emails from yesterday. But of course your opponent, your adversary, will be able to change the input and basically spammers will be able to learn what gets blocked and try new things, right? So that's really what I mean by the state of the environment changes. So you want to still be able to block the spam from yesterday. You want those to still be blocked today, but you want new sort of updated spamming to also be blocked. I have no idea how I'm doing time, by the way. So. Yeah, go ahead.
Yeah, in the case before, when you said if the environment changes over time, then you would probably want your learning rate to change less So like before you showed that you have square root t
Yeah.
on the bottom, but then if it actually changes fast enough, then you won't be able to catch up.
Yeah. Yeah, so this is an issue, and it's not really covered very well with this notion of regret, because regret really measures your rate of success with one sort of fixed special theta, right? But that one fixed special theta may not be the same special theta for your entire sequence. So yeah, so it's a bigger issue, but you're absolutely right. I think I skipped to the next slide. Okay, that's good. So it's you just run your whole online learning algorithm, and you just treat your IID dataset as though it's some ordered sequence. I mean, there's nothing there to stop you, right? There's nothing really wrong with that. And then you just train as though you were actually training some online learning scenario. And then what you do is you just wait all the way at the end, and you just take the weights that you end up with, right? It's a very simple way of doing it. However, why would these final weights actually be optimal? And in fact, they're not. I'll show you that they're not. And this other problem is we calculate these gradients on one single data point. So we have way too high variance for this to make sense, right? At least that's what I feel naively is the problem. And remember that online gradient descent, from the definition of that thing, like really, why would we expect this to work at all?
I have a question. If you consider each example as your data set, doesn't that mean that your bias is too high?
Each example?
Yeah, so you consider, even if you have only a few examples, I don't see how the variance is so high. Isn't the bias is the problem?
Well, okay, so what I mean by variance is that, okay, let me be a little bit more precise. So the specific values for these gradients, they're volatile, they flip-flop, they go all over the place. That's what I mean by that. Alright, so now so I'll be a bit quick here. So how am I doing with the time?
20 moments.
Okay.
So usually when you look at these samples one time, usually I going to be just moving in like one dimension instead of many dimensions, because you probably want to take the principal component of the variation, or basically what the biggest signal you're getting from that one sample. If you get quite a few, usually you can get let's say a better average vector.
Right.
But on the long term, mini batching is just a good technique for saving time.
Yep.
Actually do the
There's more to mini batching than just saving time, right?
Yeah, so it's more efficient, let's say. Right?
Yeah, but it actually can lead to a better
There's a result which is saying that the same result.
Okay. Yeah, I mean asymptotically they're always going to converge to the same value, right? But all right, let me just dive in here. So the answer that I really want to the question that I really want to answer here is, why do we expect this online to work for batch learning? So why do we think this is a good approach at all? So for this I'm going to have to supply a little bit of theory background, because otherwise it's that's just the way I understand things, really. I mean, I can come up with all sorts of excuses, but this is just the way I think. So please bear with me. So what is the idea of this follow the leader? So the idea really is to sort of adjust course now, which means at round t, little t, but in a way that would also optimize prior loss. So that's a little bit funny how. Okay, so what is follow the leader? So forget about the regularized for a second. The update really is, so what we want to do is we want to minimize the sum of all of the losses that you incurred so far and that's going to be my new weight. So it's kind of a greedy approach. Now what is followed a regularized leader is just where we take this exact same approach, but we add a regularization to it. This can be all sorts of different terms, but right now I just use the most generic one, which is an L2 term. And so this is really how you would phrase follow the regularized leader. And it's just a way of phrasing the problem. I will show how this actually reproduces online gradient descent. Oh, by the way, I use these kinds of losses interchangeably, so that's why I put this little box here. By LS of theta, I actually really mean L evaluated at data point S. Oh, by the way, these are some nice reviews if you want to read them. Especially the bottom one is really good. I found actually that a lot of this online learning actually happens in Israel. I don't know why, but it's your national pastime, I think. Okay, so let's go one step back. This is just calculus. So remember how this power series expansion works. You want to evaluate the function at A, but you know it at B. So what do? Is you correct for it. So first you say they're the same, then you say actually they were a little bit different, actually they were a little bit different. So you keep sort of, and if A and B are close to each other, then all of the sublinear corrections are small. Now, if a function is convex, how you can think of it is that the rest term is something positive. So in this so-called subgradient formulation, what you can do is you can sort of set a linear upper bound. And how does this work? So first we define our regret again, but now what we did is we added this regularization term. That's all that we did. So far this should be familiar, right? So this is just a single data point loss. Single data point loss at this special magical theta star, and this is the L2 regularizer and the L2 regularizer at the special value again. Now, what is the linear upper bound that I'm talking about? It's this thing. So why can I do that? If that function is convex, what I'm basically saying is that this thing will be something positive. So the difference in these is the difference in these. That's sort of a quick way.
Is the difference? It's bounded by the difference on those numbers.
So the difference. So it really is about. It's a statement about the difference between the same function that evaluated at different points. Okay. And so think about. So a convex. Really, what I mean is this, right? Yep. A function that kind of does this. I can also just have my face. And if I evaluate my function here and I evaluate my function here and I draw a straight line through it, then everything that's in between them, so a straight line that goes through my head, that will always be on top of the rest of the curve that's in between them. That's really what I'm saying. I just realized I had to draw a graph here. Okay, so now FTRL, I'm writing it down in a very suggestive way. I'm saying my next set of weights is the argmin of my regret that I incurred up to that point, relative to this special point here. Now, this special point, luckily, doesn't really matter because when we want to take the argmin of this thing, it becomes a constant, right? It becomes something that's independent of theta. So who cares? So what's really happening here is this new data point, this new set of weights, is really well approximated by this nice linear approximation. Now, the rest is very simple. What you just do is you just actually evaluate this. So you take the derivative, you set it to 0. What you end up with is this guy. And if you write it down into a recursion relation, this is exactly what online gradient descent is. You like that? I really like it. So the reason why is because why is this thing minimizing regret? No idea, right? Actually, now you have an idea because it actually says it explicitly here. We minimize regret. Now we don't minimize full regret up to big T, and we're cheating a bit because we're evaluating all these things at specific data points. So that's where we're cheating, that's where we're losing some power. Other than that, this is exactly why you can expect this thing to work. Okay, so in short, FTRL attempts to minimize regret explicitly, albeit greedy. Okay, so if you want to say something bad about FTRL, that's it. FTRL is a general framework that encompasses many algorithms, including the simplest things you can do, which is online gradient descent, but it really encompasses a lot more. There's really, and that's one of the surveys that I listed before. Really shows you all of the different algorithms that you can sort of derive from FTRL. So FTRL picks the weight at each round in such a way that each round gets closer to the special value theta star. Right? Am I in the way, by the way, if I keep walking through the screen? No? Okay. So that's why I'm saying, so I guess this is really where I wave my hands a bit and say, like, this was convincing to me at least at first. To say, okay, so this must be a good candidate for batch optimization. Because we're working towards one special value that we're trying to optimize for. We don't care about how all of the different weights may change. Eventually we want one set of weights. Now, whenever you mention FTRL, people are always a little bit disappointed because they really hope that you explain this adaptive FTRL proximal algorithm, which I can totally do. I have slides, but I put it all the way at the end because I don't think it really fits in this. But if you want it, let me know. I'm happy to. Right, so online to batch conversion. How do we use online learning now? So now I've sort of waved my hands a little bit and say, like, okay, so maybe actually this might work, right? So how do we use it as a tool for batch learning? That's really the question that I want to answer. Now, some choices. I guess one of the simplest choices is to just take the average of all of the ways that you've seen so far. Why not? And actually, you can show that that the loss is bounded by the regret explicitly with this choice, which is really nice. As it turns out, there's a better approach, which is where you take the last k, which is just a subset of the smaller than big T. Either. So basically, you do online learning, you keep going, and then at some point you say, actually, now I want to start recording all of my weights, and then I take the average of all of that. And that's already, that performs a lot better. And the thing that I really want to advocate is, why not just take the last one? Because I'm stupid, I want to do the stupidest thing, and I'm not stupid, but I'm lazy. So, here are some nice papers that actually address this. Again, by some Israeli people. Names are difficult for me, so I'm really apologizing. Is it Shamir? I think you mentioned it? Yeah. So I think this is Ohad Shamir. I think they're both actually. Anyway, okay, so sorry. So here I show. So on average, the loss that you can expect compared to the sort of perfect scenario. For this case, so this is just averaging everything. Is log t over square root of t. So this is for strongly convex, in the generally convex case. Otherwise the denominator is different, but I don't want to really cover that case. So it doesn't really matter either. So the point here is this. This is the optimal solution. So this thing. So this thing where you say, okay, now you start recording, and then you start recording all of it until the end. That's the thing that is optimal. And there are other ways that you can also get to this optimal kind of optimization error.
Is it not dependent on alpha?
Yeah, it is, yeah. Yeah, it totally is. I mean, I'm skipping so many details here, but yes, it is, of course. Then here, I say, okay, you know what, it actually isn't all that great. But really, is it so bad? Log is fine, right? At least that's what I think. I think, oh log, alright. So what's the take-home message that I really want to say? I want to say, okay, taking this last iterate, okay, sure it's suboptimal. But I would say it's only marginally so, right? Log. Come on. Amongst friends. Just a log, right? Now, so I would really want to ask yourself, right? When you're at your desk and you need to do this for a business application, you need to get it ready tomorrow. Is it worth the trouble to actually do this proper online to batch conversion? So really to do some sort of fancy averaging, or will you just train your model for log 3 times longer? That's the question you need to ask yourself. I know my answer. I think you can guess what my answer is. But, that's basically what. I guess this really is sort of the take-home message that I want to convey here. I'm being very precise either. I'm being cheeky, right? So now, of course, it's not going to be complete without showing some examples from Booking.com. So we use this quite a lot, and so the list goes on and on. The examples that I chose is from 3 different departments. I guess the first example is from stuff that I've worked on myself. So this is the paid search results on Google. We have many destinations. We have many different nationalities, and we have different kinds of keywords for every single combination. So as you can imagine, it's humongous, right? All of the options that we have to take into consideration. So here I just show hotels in Tel Aviv. Sorry, it's not right to left, but I only speak this. So this we always end up on top. That's my job. So. Sorry? Are you talking about money? So what is the context here? So these paid search results, we compute the bits every single day. We compute these bits, and these bits really it's a lot of strategy goes into calculating these bits. So I can't really explain exactly how it works because it's a secret sauce and all that stuff. But what I can say is that that's a very large number of these bits that we need to recompute every day.
What are you trying to learn?
So what we're trying to learn is sort of the base prediction that we're trying to make is we want to evaluate how much each click is worth on our site. So each click on one of these search results. So if you click on this, we pay money, right? So I want to make sure that we don't pay too much. I want that if you click, that you have a high probability of booking, and preferably also an expensive booking, right? So there's a certain amount of money that comes our way after, on average, if you click that link. But we need to calculate on our side actually how much money is coming our way, and how do we extrapolate that to keywords that have never received any clicks. So that's really it's a very sparse, very difficult problem to solve. So we have a very large, and this thing runs daily. So every day we need to do this again. Now we had an old setup where we were quite happy that we could do this and even predict all of these things at full scale. So we used Spark ML, and training time was around an hour and a half. Prediction time about 2 hours, which is great, right? It's a daily job. Who cares? That's it. you can do it. Now, the current setup uses this online learning framework, which is called Focal Wabbit. Do look it up, it's really, really incredible. All of this online learning is right there. So you don't need to implement any of this yourself, you just Google this guy and a world of goodies go open. So okay, so then, so at training time, it's only about 10 minutes. And this is on a single instance, this is on a single machine. This is something that took an hour and a half before. We do it in 10 minutes, on one machine. So I hope you're impressed, because that's really why we're talking about these things in the first place, right? If this wasn't the case, then we didn't care. Okay.
Did you use a single machine for the previous setup?
No, that was a big Spark cluster. No, like hundreds of machines. No. And at prediction time, well, to be fair, for prediction time I do use as many machines as I can get my hands on, and it got it down to 2 minutes. That's just latency, like network latencies. But this is to make these predictions on this ginormous data set. It takes 2 minutes now.
So, looking at this updated version, are you updating your bits every, I don't know, 10, 20 minutes, something like this now?
Yeah, I mean, I wish we could. I mean, we could. Theoretically, we could. But we have different limitations, unfortunately. Yeah. No, it's a very good question. Of course, we would like to.
I don't think Google updates their pricing software, so I think they do it every 15 minutes.
15 inderdaad, yeah, so 15, but that's, I mean, 15 and 24 hours, it's still better.
The reason that the old setup, the prediction time is longer than the training time is because of the limitations of the CPU.
No, it's just this data set is much smaller than this data set. So this is just a few million, a bit more. Well, but it doesn't even come close to how big this one is. And here we, because of parallelization, we don't care. Okay, so spam detection. We can't really rely on out-of-the-box spam detection, because in customer care we have a lot of booking-specific kinds of messages that we need to parse and select and filter out. And so, for instance, think about so spam is kind of the wrong word, because we also need to filter out, for instance, auto replies and receive notifications and all that kind of stuff. So really what we want to do is we want to maximize precision or recall. I forget which one, I'm sorry. But at a sort of a fixed human capacity, right? Human capacity in like how much? So 5 minutes, okay. So the approach is a very simple bag of words thing that we, well, not me, but my colleague wrote in Focal Wabbit. And the feature engineering is also done by Focal Wabbit, which is super nice because you don't really need to do anything. What it does for you, it does some n-grams, kgrams, DF, and all shebang. Okay, so now we have a nice example from front end. So this is a business case about missing children. So what is the context? So about 30% of the searches that is done by a family, like the group of customer that is a family with children. They actually don't specify the number of children that they have. Why is this? So the hypothesis is they actually forgot their children, right? It's Home Alone. This was a moving gift, but I didn't want to get it distracted. But you remember this thing where she sits on the plane and then suddenly she's like, oh, I forget his name. Right, so what are the actions taken? The actions taken is, so if we think it's very likely for a customer to be with children, we just remind them, like, hey, aren't you forgetting something? So this is on mobile, Well, so different parts of the website we have different kinds of reminders, but that's the idea. And so how do we put this into a machine learning context? So the target is really, so in this review form, the users actually tell us whether they are family or group or solo, the type of travelers they are. And what we can do is we can just build a machine learning model that guesses this traveler type, because we have the ground truth. And then what we do is we use information like location and destination, all sorts of things that we have on our side to infer what the traveler type is. Now what is the application of this? We then apply a specific treatment, which is to remind somebody that actually they're traveling with children, or aren't you forgetting something? But only when the model says that the user is actually is likely to be a family, sort of family traveling. Some details, so this is just multi-class classification. And what we use is 1 year of data, so quite a bit, not too many, but and this trains really well and it's very low latency.
Why is it 200,000 features?
So this is the cardinality of the full data set. So we just have high cardinality features. So if you think about, for instance, destination, we have many destinations. And the outcome is, so this A/B experiment was a very big success, and here you have the little boy from Home Alone finally hugging his mom at the end. So that's it for my normal material. If you want to know this FTRL optimizer, I can go on, but I think you probably have to. Okay, now that's too fast. Okay, but the slides will be shared, so you can just have a look at it yourself. I'll skip all the way to the end. Blah 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 blah. And I would like to say, well, thank you first of all, and have a look at this website, booking.ai, where we have a blog and we also have some nice links, and you can have a look at it. Are there any questions still?
How is online learning used for the missing children example?
So the way that it's trained is we're training a linear model. And linear models are very nice in when we run things in real time because it's very low latency. So what we actually do is we train this linear model and then we deploy it directly.
But that dataset doesn't change very often, so why do we need faster or online learning?
We don't. Strictly speaking, you don't really, right? You don't really need it. So, but if you, so then what do you do, right? So what other solution do you have? So scikit-learn won't help you. Yeah, you need something scalable to even be able to train a model like this. And then so online learning is kind of a, if you think about it, I mean, you're right, it's kind of an overkill, right? You're using all of this machinery for online learning and you don't really use it. You don't need it. Still, I guess what I'm trying to really convey here is that who cares? It works. Right? That's
Does it ever diverge from the correct answer because of like several bad examples and it always learns online?
So I guess I can ask, I'll answer a slightly different question, which is if you give each row sort of an importance weight, you can do that with this online learning, and then you can really create very big outliers in your gradients, right? In your output.